Welcome to the serene world of the Sleepy Brain Facts channel. Tonight, you find yourself enveloped in the tranquil embrace of winter. This season quietly reshapes our planet in ways that often go unnoticed. As the air turns crisp and the light dims, the familiar world transforms into something enchantingly different. Winter is more than just a chill in the air. It embodies a profound change, deeply rooted in the essence of physics, nature, and life itself. In this season, hidden wonders emerge. Stillness speaks its own language, inviting you to slow down and witness the intricate workings of the world. There's something almost surreal about how winter reveals dormant forces beneath the frost and the quietude. The earth, while appearing still, is alive with processes that are both beautiful and unexpected. If you appreciate these gentle explorations, consider liking, subscribing, or sharing your thoughts below. Your support helps guide others to this peaceful space, one sleepy soul at a time. For now, take a deep breath, allow your eyes to grow heavy and your body to relax. Let the soft hush of winter lull you into a restful sleep. Let's begin this journey together. Did you know that some snowfalls carry microscopic particles from space? As snowflakes form in the atmosphere, they gather more than just water molecules. High above the ground, tiny fragments of cosmic dust drift through the air. Many of these particles originate from comet tails, asteroid collisions, or the fine debris left behind when small meteoroids burn up high above. When conditions align perfectly, forming crystals can capture these particles, encasing them in layers of ice before they settle on the ground. Later, when snow from remote regions is carefully melted and filtered in laboratories, researchers may uncover these otherworldly grains. Under a microscope, they reveal exotic minerals, glassy beads forged by intense heat, or compositions that hint at distant origins within our solar system. In this way, winter transforms into a quiet delivery system for materials that have traveled across interplanetary distances. While most of us see only a white blanket covering the ground, hidden within it lies a record of events that unfolded far beyond our planet. Extremely cold weather can also create unique sounds that simply do not exist in warmer climates. On the coldest winter days, you might hear the sharp, squeaking crunch of footsteps in dry, powdery snow. This unique sound fades away as soon as the temperatures rise. It emerges from rigid snow grains that rub and fracture under pressure, a phenomenon that requires both low temperatures and specific crystal structures. Beneath the frozen surfaces of lakes and rivers, you can experience deep booms, cracks, and echoing pings. As temperature fluctuations cause the ice to expand and contract, these vibrations travel through the ice and the water below. They often carry for long distances, creating an eerie chorus that fills the quiet landscapes. Even the thinnest ice on puddles can shatter into chime-like tones if disturbed in just the right way. In extremely cold, calm air, distant sounds can travel farther and appear sharper. This happens because sound waves bend and bounce differently in the stratified atmosphere. Together, these elements create a sonic environment that is distinctly seasonal, a collection of sounds that belong exclusively to winter, falling silent as the world warms. You might also notice that winter can cause rivers to temporarily reverse their flow. Under certain conditions, a mix of ice, wind, and water levels can push currents in the opposite direction of their usual path. Each of these phenomena contributes to the rich tapestry of winter's auditory landscape. Ice jams play a significant role in certain natural behaviors. When broken ice accumulates and becomes lodged in a narrow section of a river, it creates a temporary dam. This blockage causes the water behind it to rise, compelling it to find a new path. If additional water continues to flow from upstream, you may notice the surface flow moving upstream as the system attempts to balance the pressure. Strong, persistent winds sweeping across wide river mouths can also push water into inlets and estuaries. This action raises the water level just enough that gravity momentarily favors an inland direction. However, once the wind calms, the ice jam breaks, or the water level stabilizes, the river returns to its normal flow. To those observing from the shore, it can appear as if the river has defied gravity and changed its course. On the coldest nights, the chemistry of the air around you can shift dramatically. When temperatures drop and winds ease, the lower atmosphere can settle into distinct layers. Cold, dense air pools close to the ground, while warmer air rests above it. This phenomenon, known as an inversion, acts like a lid over the landscape, trapping gases and particles near the surface. Pollutants from vehicles, heating systems, and industrial activities accumulate instead of dispersing. In this concentrated cold environment, chemical reactions behave differently. Some reactions slow down as thermal energy decreases, while others become more efficient because the reactants are closely held together. Nitrogen oxides, ozone, and fine particulates can reach levels that change both the composition and optical properties of the air, sometimes giving winter haze its unique color and texture. Natural emissions from soil and vegetation also respond differently, rising into an atmosphere that doesn't mix them away quickly. As a result, the invisible mixture entering your lungs on a still, bitter night can be chemically distinct from what fills the same streets on a breezy, mild afternoon. Winter storms can generate electrical charges that are stronger than many summer thunderstorms. In certain intense systems, particularly those that produce heavy snow, the turbulence and collisions inside clouds create ideal conditions for separating electrical charges. Ice crystals, sleep particles, and soft hail, known as grapple, bump, and rub against each other in powerful updrafts, transferring charge in the process. As you reflect on these phenomena, consider how they shape the world around you. Would you like to explore more about these atmospheric changes, or perhaps take a moment to rest? As time passes, areas of strong positive and negative charge within a cloud begin to drift apart, creating an electrical imbalance that can eventually bridge the gap. This phenomenon results in flashes of lightning appearing within swirling snow, illuminating a sky that would typically remain dark and muted during a blizzard. Often referred to as thunder snow, this event tends to occur in localized, highly energetic storms, particularly near large lakes or coastal regions where warm water fuels vigorous convection in cold air. Snowflakes scatter light differently than raindrops, giving these flashes a unique appearance that can make them more challenging to detect. You might notice a flickering glow that diffuses through the thick snowfall, creating an enchanting visual effect. In freezing temperatures, the way light interacts with the landscape can shift dramatically. Fresh snow reflects most of the sunlight that touches it, transforming open ground into a bright, almost glowing surface that rivals the brilliance of sandy deserts. This high reflectivity changes the balance between incoming and outgoing energy, cooling the air just above the surface and affecting how air layers develop. Additionally, temperature gradients near the very cold ground can alter the way light bends as it travels, subtly shifting the perceived position of distant objects. This interplay of light and snow creates a captivating and mysterious atmosphere, inviting you to explore the beauty and complexity of winter storms. Under the right conditions, you can witness the extraordinary. Bending light can stretch, lift, or distort horizons and structures, creating the illusion of far-off features, shimmering or floating. Ice crystals suspended in the air act like tiny prisms and mirrors, scattering sunlight into halos, pillars, and veils of brightness that hover gracefully above snowy fields. Even artificial light takes on a new character as the glow of the city travels farther over reflective snow and low clouds, illuminating the night sky in ways that sharply contrast with summer scenes. This interplay of altered reflection, scattering, and refraction transforms winter into a season where the familiar rules of light seem to shift. It's a time when hidden physics comes to life, revealing phenomena that remain invisible in other seasons. As temperatures plunge far below what we consider normal, everyday substances enter states we rarely encounter in our daily lives. Liquids thicken and creep rather than flow, while gases lose energy, causing their molecules to barely move. In these frigid conditions, tiny forces, usually drowned out by heat, begin to matter significantly. At sufficiently low temperatures, some metals allow electrical current to glide through them with almost no resistance at all. As you reflect on these wonders, consider how winter invites you to see the world anew. Will you embrace this season of transformation? Imagine a world where wire transforms into a nearly perfect highway for electrons. In this fascinating realm, magnetic behavior shifts as materials switch states, all while thermal motion quiets down. Even something as simple as water reveals its intriguing nature, creating various types of ice, each with unique crystal structures and mechanical strengths. For scientists, winter becomes an outdoor laboratory, providing long stretches of cold that would typically require complex equipment. It serves as a gentle reminder that our everyday surroundings hold secrets that emerge only when the planet lowers the thermostat. In certain regions, snow can form without ever touching a cloud. On the coldest, clearest days, tiny ice crystals materialize in the air, sparkling in the sunlight against a backdrop of uninterrupted blue. This enchanting phenomenon is known as diamond dust. It occurs when the air near the ground is extremely cold and still, yet retains a hint of water vapor. Instead of gathering in high clouds, the water molecules arrange themselves directly into ice, nucleating around microscopic particles or forming spontaneously. As you reflect on these wonders, consider how nature's quiet transformations remind us of the hidden complexities in our world. Imagine each crystal, small and often shaped like a delicate plate or needle, gently falling through the air. They descend so slowly that the atmosphere feels like a silent shimmering mist. At night, streetlights transform these particles into glowing pillars and halos, casting an enchanting glow over familiar streets, making them seem almost unreal. When aircraft, chimneys, or human movement disrupt these fragile fields of crystals, they carve invisible paths through the air. This phenomenon blurs the line between mere weather and a captivating atmospheric display. Winter possesses a unique ability to alter the sky's colors in ways that no other season can. As the sun hangs low over a cold horizon, its light must traverse a thicker layer of atmosphere before reaching your eyes. Along this journey, it encounters an increased number of air molecules and tiny particles, including more ice crystals suspended in the upper layers. The shorter wavelengths, like blues and violets, scatter away more efficiently, leaving behind the warmer reds and pinks that beautifully wash over the sky at sunrise and sunset. Moreover, cold air holds less moisture, often rendering the atmosphere clearer. This clarity diminishes the hazy veil that typically softens summer colors. The result is a twilight that appears sharper and more saturated, showcasing deep cobalt hues overhead, contrasted with vibrant bands of orange, crimson, and purple near the horizon. Take a moment to appreciate this exquisite transformation. Would you like to continue exploring, or perhaps take a moment to rest? In the polar regions, the sun often barely rises or sets for long periods. This phenomenon creates a unique effect, stretching into prolonged dawn-like or dusk-like glows that linger for hours. High-altitude ice crystals play a fascinating role, refracting and reflecting this tinted light into arcs, pillars, and subtle glows that are seldom seen during warmer months. As the temperature drops, ordinary materials begin to behave unexpectedly. Rubber, which bends easily in summer, becomes rigid and brittle in the deep cold, snapping with a sharp crack instead of stretching. Plastics, typically tough and resilient, may suddenly fracture under loads they would normally withstand. Metals can contract enough to alter the fit of moving parts, tightening joints, changing clearances, and shifting mechanical tolerances in machines and buildings. Lubricating oils thicken, causing gears and bearings that usually spin freely to slow down. Even everyday objects like glass can react differently, becoming more prone to thermal stress if one part is warmed while another remains frigid. On a microscopic level, cooler temperatures reduce thermal motion inside solids, making atomic lattices less forgiving when they are forced to move or deform. Take a moment to reflect on how the cold transforms the world around you. It's a reminder of nature's intricate balance and the unseen forces at play. Would you like to explore more about these mesmerizing changes, or perhaps take a moment to rest? When engineers work in cold climates, they face a unique challenge. They must carefully choose materials, shapes, and tolerances that can perform well across a wide range of temperatures. If you pay close attention, winter presents a fascinating illustration of how the properties of materials are influenced by their environment, rather than being fixed traits. Picture this: snow can fall even under clear skies. This phenomenon occurs when tiny ice crystals form in air that is so cold and stable that clouds never get a chance to develop. Near the ground, the atmosphere can retain just enough moisture for these crystals to gather on microscopic particles, drifting downwards with barely a ripple to disturb them. The result is a delicate, glittering snowfall that seems to emerge from thin air. These occurrences are most prevalent in open plains, polar regions, and high-altitude areas where temperatures drop sharply and the atmosphere stays extremely dry. At night, streetlights can illuminate these falling crystals, revealing countless pinpoints suspended in still air. It creates the illusion that the sky is producing snow, even though it remains cloudless. Because these ice particles are so small and lightweight, they can linger for quite some time, often settling without forming a thick layer of accumulation. Take a moment to reflect on this enchanting aspect of winter. Consider how the interplay of temperature and moisture creates such mesmerizing displays. Wouldn't it be wonderful to explore more about how nature shapes our world? You notice how sensitive they are to the slightest disturbance. Footsteps, passing cars, or even a sudden breeze can scatter them effortlessly. This snowfall reveals that precipitation doesn't always require towering clouds. It can form quietly in the lowest layers of the atmosphere when conditions are calm, cold, and pure enough for ice to assemble from vapor. Winter winds carry particles much higher into the atmosphere than summer winds. When cold air masses sweep across vast areas, they create powerful pressure gradients that promote strong upward motion at specific points. Over open snowfields, the wind can lift fine crystals from the surface and inject them into fast-moving layers above. These currents can transport airborne particles like dust, salt, or tiny fragments of organic matter far higher than they would typically reach during the warmer months. In winter, the atmosphere undergoes significant changes as well. The boundary between the cold air near the ground and the warmer layers above can create zones where winds accelerate sharply. This allows small particles to hitch a ride to altitudes usually achieved only by more violent forces. As you reflect on this, consider how nature's delicate balance reveals the beauty and complexity of our world. You might feel inspired to explore further, or simply take a moment to appreciate the quiet wonders around you. As summer transitions into winter, a fascinating process unfolds. Once airborne, materials can drift for great distances, sometimes traversing entire regions before settling back down. Scientists harness this phenomenon to explore how nutrients and minerals move across continents. During winter, the air can carry unique signatures from soil, vegetation, and sea spray, lifting them upward and outward. The combination of powerful lifting forces and lightweight particles makes winter an unexpectedly effective transporter of atmospheric materials. Some animals undergo remarkable transformations during this season, adapting so drastically that they appear to be entirely different species. The cold compels many creatures to enter states that seem unimaginable for humans. For instance, certain mammals adjust the thickness and insulating properties of their fur. Yet, these adaptations run much deeper. Several species alter their metabolic pathways to conserve energy, utilizing stored fat in a slow, controlled manner that enables them to survive extended periods with limited food. Others even lower their heart rates to a fraction of their usual pace, sharply reducing oxygen demand and shifting their tissues into a completely different operational mode. Remarkably, some amphibians can withstand ice forming within their bodies by controlling where the freezing occurs and producing protective compounds that prevent cellular damage. Isn't it intriguing how life adapts to the harshness of winter? As you reflect on these extraordinary adaptations, consider how nature continually finds ways to thrive against the odds. Even birds experience transformations. Some adjust their internal organs, either shrinking or enlarging them based on their need to extract more energy from food or to lighten their bodies for long migration flights. These changes are so significant that these creatures behave like different versions of themselves, optimized for the cold rather than warmth. Winter reveals the incredible adaptability of biology, showing how living organisms can reshape their inner workings in response to environmental demands. In deep winter lakes, layers of water often remain unmixed. As the cold sets in, the surface of the lake cools until it reaches the temperature where water is densest. When this water sinks, it creates a stable layer beneath the lighter, slightly warmer water that hovers just above freezing. This arrangement can lead to a stack of layers that refuse to blend, even when winds sweep across the surface. Eventually, when the lake freezes, the ice cover locks this entire system in place. Light can still penetrate through the clear ice, allowing algae and microorganisms to thrive in the upper layers, while deeper regions remain shrouded in near total darkness. Nutrients released from the sediments at the bottom accumulate slowly, untouched by disturbance. Isn't it fascinating how life adapts, even in the harshest conditions? You might find comfort in knowing that resilience is a part of nature's design. As you reflect on these transformations, consider how they resonate with your own experiences. Would you like to continue exploring this theme, or perhaps take a moment to rest? As you explore the depths of a lake, you notice that oxygen at the surface struggles to reach the lower waters. This creates pockets with distinct chemical compositions, even when they are close together. These layered environments resemble miniature oceans, each with its unique internal structure, circulation patterns, and seasonal cycles. When spring arrives and the ice begins to melt, the entire water column mixes. This mixing releases nutrients, carbon dioxide, and other trapped materials into the upper layers of water. The winter's layering dynamics significantly influence the biology of the lake for the rest of the year. You may also find that freezing soil can rise with enough force to shift heavy structures. This phenomenon starts when moisture in the ground moves toward freezing fronts. As water freezes, it expands, creating pockets and lenses that push the surrounding soil upward. This process continues as more water is drawn in, promoting further growth. Over time, these icy formations can elevate the surface by several centimeters, exerting considerable upward pressure. You might see buildings, roads, and fences shifting, tilting, or cracking as a result. This movement is especially common in regions that experience repeated freeze and thaw cycles, where the upper soil layers fluctuate around the freezing point. Take a moment to reflect on the intricate interplay of nature and how it shapes our environment. Would you like to continue exploring this fascinating topic, or perhaps pause for a moment? Different types of soil react uniquely to environmental changes. Clays and silts retain more moisture, which leads to significant shifts in their volume. In contrast, sandier soils are less affected by such changes, yet they can still rise under certain conditions. Engineers take these factors into account when designing foundations, often extending them below the expected freeze line or selecting materials that can accommodate movement. As you observe the ground during winter, frost heave serves as a reminder that the surface is not static. It is a dynamic layer that responds dramatically to variations in temperature, moisture, and structural changes. While winter can bring entire ecosystems to a standstill above ground, life continues to thrive below. Plants may halt their growth, insects might vanish from sight, and many animals retreat into hidden shelters. Yet the soil beneath the snow remains surprisingly vibrant. A thick layer of snow provides insulation, trapping warmth from the ground and preventing extreme temperature fluctuations. This creates a protected environment where microorganisms remain active, breaking down organic matter and releasing essential nutrients that plants will depend on when spring arrives. In this hidden realm, small burrowing mammals carve out tunnels under the snow, foraging for seeds, roots, and even each other in a secret world that remains unseen from above. Take a moment to appreciate the intricate life beneath the surface, even as winter blankets the landscape. Fungi play a vital role in the ecosystem, breaking down leaf litter and fallen wood. They recycle materials that nourish the forest floor. Beneath frozen streams, aquatic insects remain active, feeding and growing until the warmer waters return. Even the roots of plants engage in tiny chemical exchanges with soil microbes. Although the surface landscape may appear still, underneath, a quiet engine of life continues to thrive. Winter creates a fascinating division in the ecosystem. One layer seems frozen in time, while the other keeps the momentum alive, preparing the landscape for the next season. Snow crystals form in a variety of shapes, shaped by tiny changes in temperature. The structure of each crystal reveals the intricate relationship between temperature and humidity as it forms in the atmosphere. You may notice plates, needles, hollow columns, and complex branching patterns arising from these subtle shifts. When the air warms slightly, crystals grow broad and flat. In colder conditions, they elongate into slender shapes. Small changes in humidity affect how quickly different facets develop, influencing the symmetry and complexity of each unique piece. The beauty of this process invites you to reflect on the hidden life that continues even in the depth of winter. The atmosphere is never completely uniform, and a single snowfall can reveal countless variations. Scientists delve into these intricate structures to grasp the atmospheric conditions, as each snowflake holds a record of the environment in which it formed. Even within a single snowflake, different sections can develop under slightly varying conditions as the crystal tumbles through shifting layers of air. This results in a collection of tiny sculptures, each shaped by the laws of physics. Each flake emerges from a sequence of microscopic events that will never unfold in the same way again. It becomes a natural gallery of design, crafted one molecule at a time. Freezing fog can create ice coatings that grow thicker than the fog itself. This phenomenon occurs when supercooled water droplets linger in stable air and cling to any surface they encounter. When these droplets touch objects like tree branches, power lines, or fences, they freeze instantly, forming a delicate layer of ice. As the fog continues to flow, more droplets settle and freeze, leading to a buildup known as rime. Because this process can persist for hours, the resulting ice may become surprisingly thick, even though the fog layer contains very little moisture. Take a moment to reflect on the beauty of these natural processes and consider how they shape the world around you. Ice accumulates in delicate, feathery structures that extend outward with the wind. These formations create intricate patterns that appear almost handcrafted, yet they arise from atmospheric conditions alone. Unlike clear ice formed from freezing rain, this porous, structured ice, known as rye ice, is lighter but still has the capacity to weigh down branches and cables. In areas where winter fog is common, landscapes can become coated with pale, spiky growths that seem to appear overnight. This phenomenon illustrates how persistent, small droplets can dramatically transform the environment when temperatures dip below freezing. The cold of winter unveils thermal patterns across the planet that satellites often struggle to detect. As night falls, especially under clear skies, the ground can cool rapidly. Different surfaces release heat at various rates. Rocks, soil, vegetation, and man-made structures all respond to the chill in unique ways. This creates a patchwork of temperatures that becomes visible only when everything is exposed to that intense cold. Researchers take advantage of these winter conditions to study heat retention, moisture content, and the properties of materials across large areas. The contrast between warm and cold surfaces is more pronounced during this season than at any other time of year, offering valuable insights into our environment. Take a moment to consider how these subtle shifts in temperature and structure can reveal the intricate balance of nature. Would you like to continue exploring, or take a moment to reflect? Winter unveils a unique world through its thermal signatures. You notice how landscapes absorb sunlight, how cities trap warmth, and how various ecosystems manage energy in the face of harsh conditions. Even the patterns of wildlife emerge from these cold night readings, as animals subtly alter the thermal footprint of the ground beneath them. In this way, winter becomes a diagnostic season, revealing differences that often remain hidden when the environment is warm and uniform. The quiet clarity of extreme cold acts like a spotlight, illuminating the hidden structures of our world. Some insects have developed remarkable strategies to survive the winter. They avoid death by carefully removing water from their bodies, a technique known as freeze avoidance. As temperatures drop, these resilient creatures begin to convert internal substances into forms that draw water out of their cells. By lowering their water content, they prevent the formation of harmful ice crystals. With so little liquid left to freeze, these insects also produce special compounds that lower their freezing point, allowing them to endure temperatures that would devastate most living tissues. Consider how these adaptations reflect the resilience of life in the cold. The next time you step outside into the winter chill, take a moment to appreciate the intricate dance of survival happening all around you. If you're ready, let's continue exploring these fascinating adaptations, or take a moment to rest in this serene reflection. In the heart of deep winter, a remarkable transformation unfolds. As the frigid air settles in, the bodies of insects enter a profound stillness. Their heart rates slow dramatically, metabolic processes drop to a bare minimum, and all movement halts. Yet these tiny creatures remain very much alive. When warmth returns, a shift occurs within them. Water re-enters their tissues, metabolism sparks back to life, and the insects carry on as if the long, harsh winter was merely a brief interlude. This incredible adaptation illustrates the lengths to which evolution will go to ensure survival, even in conditions that seem utterly inhospitable. Snow cover holds the power to influence weather patterns thousands of miles away. When the landscape dons its bright reflective coat of snow, it bounces much of the incoming sunlight back into space instead of absorbing it. This rapid cooling of the surface changes the temperature and pressure dynamics above, creating pockets of cold, dense air that behave differently from the warmer surroundings. Storm systems take notice of these shifts as they navigate along pathways shaped by contrasts in pressure. As the snow-covered areas expand or contract, these corridors adjust, guiding storms toward new routes. This intricate dance between snow and storms highlights the delicate balance of nature, where even the smallest changes can have far-reaching effects. Imagine a snow-covered landscape acting like a vast mirror. This serene expanse cools the atmosphere across entire regions, reinforcing pressure systems that linger for days. You may not realize it, but this phenomenon redirects storms over continents, influencing where moisture falls and how powerful weather fronts become. It even determines which areas experience unusual weather patterns. Meteorologists pay close attention to snow cover because it creates ripple effects that extend far beyond the snowy terrain. These winter landscapes play an active role in shaping weather, guiding storms that may originate thousands of miles away. As night falls in winter, something fascinating happens. The cold air carries sound much farther than it does in summer. This is due to the way sound waves travel, especially when there's a stark temperature difference between the ground and the air above. On winter nights, the surface cools rapidly, while the air just above remains warmer. This situation causes sound waves to bend downwards, allowing distant noises to reach you clearly. In fact, sounds can travel multiple times farther than they would during warmer seasons. As you reflect on these intricate connections, consider how the winter landscape influences not just your immediate surroundings, but also the world beyond. Would you like to explore more about the wonders of nature, or take a moment to pause and appreciate the beauty around you? The stillness of winter nights deepens the experience around you. The snow-covered ground absorbs many sounds, while it also muffles the wind and surface activities. This creates a serene backdrop, allowing human-made noises from trains, vehicles, and machinery to resonate more clearly. Natural sounds, too, like the cracking of ice or distant wildlife, can travel surprising distances, making this season a unique auditory landscape. As temperatures drop, winter transforms not only the scenery, but also the very fabric of the air. It acts as a natural amplifier, unveiling a distinct acoustic character that is rarely perceived during warmer months. In this frosty season, ice crystals can create halos and pillars that are seldom seen when temperatures rise. When sunlight or moonlight filters through these suspended ice crystals, they refract and reflect the light, forming intricate geometric shapes. During especially cold and stable conditions, the atmosphere can be filled with millions of tiny crystals shaped like plates or columns. These delicate structures align themselves gently with gravity as they drift. When light enters one side of a crystal and exits through another, it bends at precise angles, producing arcs, rings, or tall pillars of brightness above streetlights. As you immerse yourself in this winter wonderland, take a moment to appreciate the beauty and stillness that surrounds you. Perhaps you feel inspired to explore further, or simply to pause and reflect on this magical season. You observe formations that take the shape of glowing circles around the sun or moon, while others emerge as sharp vertical beams resembling illuminated towers rising from the ground. The appearance of these shapes varies based on the type of crystal and the angle of the light source. Winter creates an ideal environment for these breathtaking displays, as the cold air can sustain numerous crystals without melting them. The outcome is a stunning array of visual phenomena that transforms familiar skies into captivating scenes filled with optical geometry. As you look out over frozen oceans, you might hear booming sounds that travel remarkable distances. When sea ice stretches across vast expanses of ocean, it acts like a flexible sheet, responding to stresses from tides, currents, and changes in temperature. As the ice expands or contracts, it can fracture suddenly, producing cracks that release bursts of sound. These noises can range from sharp pops to deep resonant booms, echoing across the frozen surface. Some intriguing events occur beneath the ice. Trapped pockets of water may shift, or pressure may redistribute along ridges where the ice has accumulated. Because sound travels efficiently through both ice and water, these vibrations can resonate over impressive distances. Take a moment to reflect on the wonders of nature and the extraordinary sounds that accompany these frozen landscapes. In the polar regions, you often hear explorers and researchers describe an eerie symphony of long, drawn-out groans and rumbling tones. These sounds seem to emerge from nowhere, born from the slow movements of the pack ice. Each tone conveys vital information about the thickness, temperature, and stress of the frozen landscape. The ocean, now a vast resonating body, communicates its constant adjustments. As winter settles in, temperatures shift the delicate boundary between land and atmosphere. The ground cools deeply, altering how heat and moisture exchange between the surface and the air. A layer of frigid, dense air clings close to the ground, creating a stable boundary that resists mixing with the warmer air above. This boundary changes how winds behave, how humidity moves, and how gases circulate. In some areas, it can trap pollution or moisture, leading to the formation of fog, haze, or frost. In contrast, other regions may experience exceptionally clear air with remarkable visibility. When soil freezes, it halts the release of moisture and heat that usually contributes to atmospheric dynamics. As a result, the atmosphere loses a crucial source of input. Over time, a new balance emerges between the land and the sky. Winter, in its quiet yet powerful way, redraws the interface between Earth and its atmosphere, altering the rules of heat and moisture exchange. As you reflect on this transformation, consider how nature continuously reshapes our world. If you wish to delve deeper into this topic or take a moment to pause, the choice is yours. This shift influences everything from storm formation to regional climate patterns, marking one of the most significant seasonal transitions on our planet. Snow acts as a natural insulator, allowing plants to endure even the harshest cold. A layer of snow captures warmth from the soil, preventing rapid temperature fluctuations, and meet cold from the soil, preventing rapid temperature fluctuations, and meet cold from the soil, and meet cold from the soil, and meet cold from the soil, and meet cold from the soil. While the air above may drop far below freezing, the ground beneath a thick blanket of snow can stay close to freezing, creating a stable environment where roots and microbes can maintain some activity. This insulation safeguards plant tissues that would otherwise succumb to extreme cold. In forests and meadows, snow cover serves as a protective layer, enabling seeds, dormant buds, and root systems to survive conditions that the open air cannot withstand. Additionally, this insulating effect creates a unique subnivean space, a narrow world between the soil and snow, where temperatures remain steady, allowing creatures to move safely. The survival of many ecosystems hinges on this simple yet vital physical property. Without snow functioning as a thermal shield, winter would threaten or destroy countless plants long before spring arrives. So take a moment to appreciate the profound role snow plays in nurturing life during the coldest months. Snow holds a significance that goes beyond merely blanketing the ground. It weaves itself into the biological framework that sustains entire ecosystems. When frozen, it can crack in ways that echo the patterns of Earth's continental crust. As a river's surface freezes, it forms expansive sheets of ice that shift in response to currents, temperature changes, and pressure variations. These sheets can fracture into plates with sharp edges, resembling miniature tectonic plates. As temperatures fluctuate, the ice undergoes expansion and contraction, creating ridges where sections collide and channels where they separate. This constant movement generates intricate networks of cracks that branch out, intersect, and reorganize over time. You might observe long, straight splits that stretch across great distances, or delicate webs of smaller fractures that scatter across the surface. Beneath the ice, flowing water introduces an additional layer of complexity. It pushes upward against weak spots and erodes support from below, leading to a dynamic system where the frozen surface behaves like a cold version of Earth's crust. Scientists studying the mechanics of ice utilize these natural patterns to gain insights into how stress distributes in solid materials. This exploration not only enhances our understanding of ice, but also sheds light on broader geological processes. Would you like to dive deeper into this fascinating topic, or perhaps take a moment to reflect? As you stand by the riverbank, the frozen surface before you transforms into a vibrant tapestry of tension and release. The winter sunlight reflects off the snow with a brilliance that rivals the brightest desert sands. Fresh snow boasts a high albedo, meaning it bounces back a significant portion of the sunlight that graces it. Each tiny grain of snow, with its myriad facets, scatters light in countless directions, creating a brightness that can astonish even those familiar with winter's chill. This intense reflection has a profound impact on energy balance, cooling the surface even further and establishing a feedback loop that helps maintain the snowpack. For you, the brightness can be overwhelming, potentially leading to temporary discomfort or even snow blindness if your eyes aren't shielded. In contrast, the animals that inhabit these snowy realms have evolved unique adaptations, special eyelid shapes, pigmentation, and behaviors that minimize their exposure to the blinding light. The reflective power of snow also alters the appearance of landscapes from a distance. Cliffs, Forests and mountains gain striking contrast, making distant features easier to discern. This snow-covered ground transforms winter into a season of striking visual intensity. Despite the low angle of the sun, what might initially seem like a simple white blanket is in reality a complex network of reflective structures that redirect sunlight throughout the environment. Wouldn't you agree that this intricate beauty adds a layer of wonder to the winter landscape? The cold air sharpens your view, allowing you to see much farther than in the summer. Low temperatures reduce the moisture in the air, creating dry and clear conditions when the skies are calm. With fewer water droplets and less particulate matter, light travels through the atmosphere with minimal scattering. This means distant mountains, buildings, and landscapes appear sharper and more defined than they do during the warm, hazy months. The stability of winter air enhances this clarity. Without strong rising currents or turbulent mixing, the atmosphere becomes layered and still, acting like a natural telescope that improves long-range viewing. In snowy regions, the reflective ground brightens distant slopes and ridges, further enhancing visibility. These conditions reveal landmarks that might remain hidden for most of the year. Winter transforms into a season of unexpected visual reach. While the cold may take away comfort, it offers clarity, unveiling far horizons that summer haze often obscures. In this stillness, winter can slow biological processes to near suspension. As the temperatures drop, the chemical reactions within living organisms slow down. This reduction in activity lessens energy demands and alters cellular functions. Many species depend on this slowdown to endure the harsh conditions of winter. Some reptiles and amphibians enter states where their movement nearly ceases and their heartbeats become faint. Microorganisms also scale back their activity, conserving resources until warmth returns. Plants join this seasonal shift as well. Their cellular processes change, water content diminishes, and growth comes to a halt. This state of suspension protects their tissues from freezing damage and prevents metabolic stress. The overall slowing of biological processes influences entire ecosystems. Predators hunt less, prey are less active, and the flow of energy through food webs becomes subdued. When spring arrives and temperatures rise, the renewed pace of chemical reactions ignites a burst of activity. Winter functions as a natural switch, resetting life across vast regions and demonstrating how profoundly temperature governs the rhythm of living systems. Snow accumulates in layers, preserving precise records of weather over time. Each snowfall contributes a distinct layer, shaped by temperature, humidity, wind, and the type of crystals formed. This fascinating interplay of elements reveals the intricate connections between the environment and life itself. As days and weeks pass, layers of snow compress, yet they remain distinct, each marked by subtle differences in texture, density, grain size, and even trapped air. You can imagine researchers digging snow pits, reading these layers like pages in a seasonal storybook. A fluffy layer might tell of a gentle snowfall, while a dense, rounded layer can indicate the fierce winds that compact the crystals together. Occasionally, thin crusts form when sunlight briefly warms the surface, only for temperatures to plunge once more. Dust or pollen that settles on the snow creates delicate lines, helping to pinpoint specific weather events. As you delve deeper, you notice that these layers gradually change under pressure, yet recognizable patterns persist. Each winter leaves its unique fingerprint, marked by storms, warm spells, cold snaps, and various atmospheric occurrences. This intricate layered structure becomes the foundation of glaciers in regions where snow endures year after year. What begins as delicate flakes of snow transforms into a long-term environmental record, preserved in frozen form. Ice can develop into floating sheets that collide and grind against one another, much like miniature tectonic plates. When rivers, lakes, or coastal seas freeze, the ice does not behave as a solid slab. Instead, it reveals a complex, dynamic nature. The ice forms distinct sections that respond to the currents of music, the whispers of the wind, and the shifts in temperature. These pieces may drift closer together, colliding at their edges, where they can rise into ridges or buckle under pressure. Occasionally, one layer of ice glides over another, creating formations that resemble miniature subduction zones. In areas where the ice separates, long cracks known as leads can emerge, revealing the water beneath. This dynamic interplay continues throughout the season, transforming the frozen surface into a constantly evolving mosaic. Scientists who study ice mechanics delve into these interactions to understand how stress travels through solid materials. Indigenous communities and seasoned winter travelers also learn to interpret these patterns, as the arrangement of ice sheets can indicate safe routes or warn of hazardous conditions. The shifting plates serve as a reminder that even frozen water is not static. It behaves like a living surface, responding to forces from both above and below. Winter clouds often carry more ice than water. These cold season clouds form when temperatures drop low enough for water droplets to freeze into tiny crystals. As you contemplate this intricate dance of ice and atmosphere, consider how nature's forces are constantly at play, shaping the world around you. Would you like to explore more about this captivating phenomenon, or perhaps take a moment to reflect on the beauty of winter? At these low temperatures, even small droplets can become supercooled, remaining in liquid form but ready to freeze at the slightest disturbance. Once ice begins to form, it grows by drawing from the surrounding droplets, as water vapor clings more readily to solid surfaces in cold air. This process increases the ice content in the cloud, transforming it from liquid to crystalline structures. These ice crystals can take on various shapes: plates, needles, columns, or intricate branches, depending on the specific temperature. They interact with sunlight in ways that liquid droplets simply cannot, producing beautiful halos, arcs, and other mesmerizing optical effects. The presence of ice also alters how precipitation forms. Crystals can gather moisture, grow larger, and ultimately fall as snow or sleet. Even if the ground temperature remains above freezing, the cloud itself may still be predominantly icy. This means that winter clouds operate with a different internal chemistry compared to their summer counterparts, resulting in distinctive visual and weather patterns. Cold weather can also enhance the smell of certain chemicals. As the temperature drops, the atmosphere becomes denser and less turbulent, slowing the dispersal of airborne molecules. You may notice that familiar scents linger longer in the crisp, cold air. This fascinating interplay of temperature and moisture creates a unique experience in winter. As winter sets in, you may notice that your sense of smell becomes more acute. The cold air keeps odor molecules concentrated near the ground, allowing subtle scents to linger longer than they would in warmer weather. This is especially noticeable in areas like forests, industrial zones, and even residential neighborhoods, where the aroma of wood smoke, damp soil, or fresh vegetation becomes more pronounced. In colder conditions, chemical reactions slow down. This means that certain compounds can remain unchanged for extended periods, traveling farther without breaking down. Frost and smoke can trap these odors, releasing them when the sun warms the surface, creating a unique interplay of scents in the winter air. This seasonal shift transforms familiar environments, giving them a distinct scent profile that varies with the temperature. Winter doesn't just quiet the world, it enhances specific sensory experiences by changing the chemistry and movement of air molecules around you. You might even notice intriguing patterns on frozen lakes during this time. Some lakes develop mysterious circular designs on their ice or water surfaces, appearing without any clear explanation. These phenomena captivate scientists and spark curiosity, reminding you of the wonders that winter brings. These rings stretch across expansive areas, their sharp boundaries contrasting vividly with the surrounding ice. Various natural processes contribute to their formation. Warm springs beneath the lake may channel heat upward, creating circular patterns as the ice thins. Beneath the frozen surface, rotating eddies of water can carve delicate spirals, which become visible when viewed from above. In certain instances, methane rising from the lakebed generates circular melt zones. These intriguing features can last for days or even weeks before gradually disappearing. Each lake possesses its own unique currents, sediment patterns, and thermal behaviors, resulting in rings that differ in shape and size. Researchers utilize drones and satellite imagery to investigate these phenomena and unravel the processes that give rise to them. For those observing from the shore or the air, the circles appear almost intentional, as if a hidden force beneath the ice has meticulously drawn them. Winter storms have the capacity to transport heat across continents. Large-scale weather systems that develop during the colder months can harness warm ocean currents, redistributing that energy over vast distances. These storms extract heat from areas with warm surface water, carry it into frigid air masses, and release it through condensation as clouds begin to form. The interaction between winter storms and our climate is profound. These storms not only reshape the structure of the atmosphere, but also alter temperature patterns downstream. As they move through the landscape, they shift jet stream pathways, impacting how warm or cold different regions become. In this way, winter storms play a crucial role in balancing global heat distribution. They act as powerful agents of energy, pulling warmth from certain areas and delivering cold to others. This movement influences ocean temperatures, atmospheric moisture, and even long-term climate trends. Each storm is a vital part of a larger global cycle, exchanging heat between land, sea, and air. Winter is not merely a local phenomenon, it is an integral participant in planetary energy transfer. Consider the snow that falls on different surfaces. When it lands on the ocean, it behaves differently than when it settles on land. In open water, the snow encounters a surface that absorbs heat and is in constant motion. Much of this snowfall melts rapidly, creating a thin layer of fresh water that floats atop the denser salt water. This fresh layer can alter the temperature and salinity of the ocean's surface, affecting wave behavior and how heat escapes from the water. When conditions turn cold enough for sea ice to form, the dynamics of snowfall become even more complex, highlighting the intricate relationship between winter storms and our planet's climate system. Would you like to explore more about these fascinating interactions? And when conditions for fermented paraving, well evli taway, beaconsord down up, and pure every beating to belodkan to arrive, snow rests atop thin ice, gently pushing it downward. This pressure allows seawater to seep into the snow layer. When this mixture freezes, it forms a unique type of sea ice, distinct from ice created directly from ocean water. Snow also serves as insulation for sea ice, slowing its growth while protecting it from melting on sunny winter days. These interactions significantly influence the thickness, strength, and movement of ice across polar regions. The combination of snow and salt water leads to phenomena that are rarely seen on land, impacting both weather patterns and ecological systems. During winter, nature creates ice lenses that bend sunlight in mesmerizing ways. When water freezes into clear, bubble-free ice, it can take on shapes that refract light with precision. Droplets that freeze into spheres on branches or rocks turn into tiny lenses, magnifying the intricate patterns beneath them. On frozen lakes, larger curved surfaces can bend and focus sunlight into bright patches that dance across the ice as the sun travels through the sky. Even slight variations in the thickness of this clear ice can create optical illusions, stretching or compressing the objects visible through the frozen layer. Under the right conditions, melting followed by rapid refreezing can produce smooth domes of ice that function like magnifying glasses, revealing the enchanting interplay of light and ice. These natural lenses unveil intricate details of the ground or water beneath, offering perspectives that are unique to this time of year. As you walk across the clear ice of a lake, you might notice stones or plants appearing in unexpected shapes, their forms distorted by the bending light that passes through the ice. Winter transforms into a season of unintentional optical wonders, a fascinating interplay between sunlight and frozen water. As the ground freezes, it captures gases that remain dormant until the thaw. During winter, the soil freezes from the surface down, trapping moisture and gases in place. Microbial activity significantly slows down, allowing organic material to lie largely undisturbed. As the freeze deepens, gases like carbon dioxide and methane, which would typically escape, remain sealed within the pores of the ice. When spring arrives and warmth returns, these gases are released in a swift pulse as the ground thaws. This phenomenon is particularly pronounced in wetlands and tundra regions, where large quantities of organic matter accumulate throughout the year. Once thawed, microbes awaken and begin to break down this material, further accelerating the release of gases. This cyclical process profoundly impacts local ecosystems, altering soil chemistry and moisture patterns in significant ways. As you reflect on this intricate dance of nature, consider how these changes shape the landscape around you. Would you like to explore more about this fascinating cycle, or perhaps take a moment to rest and absorb what you've learned? As the soil thaws, it releases gases that have been trapped all winter, creating a dynamic atmosphere. You can sense the stark contrast between the stillness of frozen months and the vibrant energy that emerges as spring approaches. This shift highlights how profoundly winter influences the movement of energy and matter beneath the surface. Once snow settles, it is far from static. Temperature variations within the snowpack cause water vapor to migrate from the warmer layers below to the colder layers above. This movement prompts individual snow grains to change shape through a fascinating process known as metamorphism. Rounded grains can evolve into larger, angular forms or transform into faceted crystals. Sometimes these grains bond together, creating stronger layers. Other times, they become weaker and more susceptible to collapse. These transformations are influenced by factors such as temperature, depth, sunlight, and the amount of air trapped between grains. Over time, the snowpack develops into a layered structure, each layer possessing its own unique mechanical properties. These changes affect everything from the risk of avalanches to how effectively the snow retains heat. Isn't it intriguing how such subtle shifts can have a profound impact on the world around you? As you reflect on this, Consider how these natural processes shape the environment you experience. You are invited to explore further or take a moment to rest and absorb the beauty of this transformation. Snow on the ground is more than just a simple frozen blanket. It is a dynamic material constantly shaped by subtle exchanges of energy and moisture. Ice can create delicate structures on plants that mimic the formations found in minerals. During winter, super cold droplets suspended in frigid air can freeze instantly upon contacting surfaces that are even slightly colder than their surroundings. When this occurs on branches, leaves, grasses, or seed heads, it leads to formations that resemble the intricate growth patterns of minerals. Rather than growing downward under gravity, the ice extends outward in the direction of the airflow, producing feathery or blade-like projections that appear almost crystalline. These unique structures rely on various factors, such as humidity, temperature, wind speed, and the shape of the plant. Even a slight change in the breeze can redirect this growth, creating layers that curve or twist as new droplets freeze. Because plants possess countless small ridges and textures, the freezing droplets attach in surprisingly geometric patterns. The result is a landscape transformed into a series of temporary sculptures. As early morning sunlight filters through, each structure is illuminated, allowing light to refract through the ice and create a delicate glow. However, as temperatures rise or winds shift, these beautiful formations are soon removed, reminding you of the fleeting nature of this winter wonderland. You notice a fascinating phenomenon. A simple interaction between plants and the cold air creates patterns that appear meticulously crafted rather than merely natural. Winter pressure patterns play a crucial role in shaping entire regional climates. These atmospheric pressure systems during the cold season dictate how air masses move across continents, significantly influencing temperature, rainfall, and storm paths for extended periods. As winter sets in, the cooling air intensifies the contrast between warm and cold regions. This contrast leads to the formation of zones where air becomes dense enough to sink and spread outwards. The size and position of these pressure centers dictate how moisture travels, where storms develop, and which areas become dry or wet. In some regions, a persistent high-pressure system can trap cold air, blocking warmer air from entering. Conversely, low-pressure patterns can steer storms toward coastal areas, while leaving inland regions parched. Even slight changes in the strength or position of these systems can dramatically reshape entire seasons. Scientists delve into studying these winter patterns because they hold sway over everything from ocean circulation to agricultural conditions. As you reflect on this, consider how interconnected our world truly is. Would you like to explore more about these fascinating interactions? Or take a moment to pause. A subtle shift in air pressure can determine whether a region experiences heavy snowfall, mild conditions, or weeks of quiet, frigid weather. Imagine frost forming intricate patterns across a window, each design a result of the interplay between temperature and airflow. When warm, moist air from indoors meets a cold window pane, tiny droplets condense and freeze, transforming the glass into a canvas of nature's artistry. As the frost begins to grow, it follows invisible gradients created by the flow of air near the glass. This results in beautiful branches, spirals, and ridges. You might notice that warmer areas remain clear for longer, while colder spots attract more ice, creating a stunning contrast. The direction of airflow from heaters, vents, or even a person moving through the room can completely redirect the frost pattern. Microscopic imperfections on the glass serve as anchor points for the ice crystals, shaping the initial pattern that spreads outward. Each pane of glass tells its own story, becoming unique due to the ever-changing conditions indoors. A shift in humidity, a sudden gust of air, or even a hand passing nearby can dramatically influence how the frost develops. When you examine these patterns closely, you uncover the fascinating physics of heat transfer, humidity, and air movement within a room. Would you like to explore more about these captivating phenomena? A simple winter window transforms into a detailed map of the world outside. The chill in the air can create mirages, phenomena typically associated with deserts. When the air close to the ground becomes extremely cold and dense, it bends light in remarkable ways, reshaping the distant landscape. Even slight variations in temperature between layers of air can cause light to follow curved paths rather than straight ones. This bending effect allows objects that lie below the horizon to appear to rise, creating a phenomenon known as a looming mirage. Snow-covered landscapes with flat horizons are particularly susceptible to this effect. Their smooth surfaces cool the air uniformly, making distant trees, buildings, or mountain ridges appear taller, sharper, or elevated above their true positions. In rare instances, layers of warm and cold air can stack together, resulting in complex distortions that make objects flicker, stretch, or seem to float. These winter mirages share a similar physics to those found in deserts, yet they manifest in environments where the air is more stable and the sky clearer. The outcome is a mesmerizing display where reality subtly shifts, illustrating just how sensitive light can be to temperature differences. As you observe these phenomena, consider how nature plays with perception and reality, creating moments that invite reflection and wonder. Ice sheets have a remarkable ability to trap ancient bacteria that spring to life when temperatures rise. In specific regions, layers of ice build up year after year as fresh snow falls and older snow compresses beneath it. Within these layers, dust, organic particles, and microorganisms become sealed, preserved in cold and dark conditions that inhibit decay. Some bacteria can enter a dormant state, allowing them to survive for extended periods without food or sunlight. When scientists drill deep into glaciers or ice sheets, they often discover these microorganisms still intact. If the trapped bacteria remain undamaged by freezing, they can be revived when exposed to warmer temperatures and moisture in a laboratory setting. Their survival hinges on protective adaptations that safeguard their genetic material and enable them to remain dormant for long stretches. These discoveries provide valuable insights into how life endures in harsh conditions on Earth. They also hint at the potential for organisms to survive in the frigid environments of other worlds. Ice does more than just preserve water. It safeguards traces of ancient environments and stores living material that showcases life's incredible resilience. Additionally, winter storms have the power to lift tiny particles into the stratosphere, adding another layer to this fascinating story of survival and adaptation. In the midst of intense winter weather, powerful updrafts emerge within large storm systems. These currents possess the strength to lift fine particles of dust, ash, salt, or organic matter high above the clouds. When these updrafts elevate the particles sufficiently, they can breach the boundary into the stratosphere, a part of the atmosphere that is typically hard to reach. Once in the stratosphere, these particles can stay suspended for extended periods, as this region lacks the turbulent mixing found at lower altitudes. This distribution of particles plays a crucial role in influencing atmospheric chemistry and can alter how much sunlight the Earth absorbs. Scientists monitor these phenomena to deepen their understanding of how winter storms contribute to the long-range transport of materials and to investigate their effects on climate. Each storm becomes a piece of a larger cycle, moving matter into areas where it can linger for months or even years. In frozen soil, animal tracks can be preserved with remarkable detail. When temperatures drop and moisture in the ground freezes, the surface hardens enough to capture impressions from passing animals with surprising clarity. While a track pressed into soft snow or thin ice may melt or distort, a track in frozen soil can remain stable for days or even weeks. The freezing process preserves shapes in the landscape, capturing delicate features like claw marks, pads, and gait patterns. You might find that researchers and wildlife trackers rely on these preserved prints to understand animal behavior, track population movements, and identify species that are seldom seen. In certain environments, brief thaws can soften the surface just enough to create perfect impressions before the next freeze solidifies them. Each track tells a story, revealing details about the size, speed, and direction of the animal. Winter landscapes offer a unique record of wildlife activity, a fleeting glimpse that vanishes when the soil thaws in spring. However, freezing temperatures can also affect materials like paints and plastics in unexpected ways. Items that perform well in warm conditions may react surprisingly when exposed to deep cold. Paints that are flexible in summer can become brittle enough to crack as the underlying surface contracts. In colder weather, the pigments and binders in paint might separate, altering their texture or adhesion. Similarly, plastics, which rely on the movement of their molecular chains for flexibility, can lose that essential movement when temperatures drop. As you reflect on these phenomena, consider how nature's cycles intertwine with our materials, shaping the world around us. Would you like to explore more about the wonders of winter? When exposed to cold, materials can become more prone to snapping or deforming under pressure. Certain plastics may shrink unevenly, leading to loose or warped joints. This happens because lower temperatures reduce molecular motion, changing how materials react to stress. As a result, designers and engineers must carefully consider these impacts when creating objects meant for winter conditions. The environment challenges paints and plastics, revealing their structural limits and reminding us that temperature can transform familiar materials into unpredictable forms. Snow dunes, for instance, can form and move like miniature desert dunes. Wind sweeping across open snowfields sculpts the surface into wave-like formations, reminiscent of those found in sandy deserts. These snow structures develop when loose, dry crystals are pushed into ridges that grow and shift with each gust of wind. Since snow is lighter than sand, even gentle breezes can shape it, creating patterns that change daily. The size of these dunes varies based on wind strength, snow type, and the terrain. Some dunes may rise only a few centimeters, while others stretch across expansive fields. As the wind continues to shift the snow, the dunes migrate slowly across the landscape, leaving behind trails of altered texture. These ever-changing shapes reveal important clues about the direction of the wind and the stability of the snowpack. Snow dunes illustrate how frozen water can respond to the same forces that shape deserts, creating landscapes that evolve continuously throughout winter. As winter progresses, ocean water can separate into brine channels with intricate chemistry. When seawater begins to freeze, the forming ice excludes most of its salt, pushing the salt-rich water into narrow channels within the ice. These pockets filled with brine create a network of winding pathways that traverse the frozen surface. The liquid inside remains unfrozen because its high salt content lowers the freezing point. As temperatures fluctuate, these channels expand and contract, altering the movement of water and salt through the ice. Microorganisms thrive in these confined spaces, forming small ecosystems uniquely adapted to extreme cold and unusual chemical conditions. The brine channels also play a significant role in how sea ice grows and melts. As brine drains downward into the ocean, it changes the density of the water below, influencing local circulation. Thus, winter sea ice is far more complex than just a solid sheet. You find yourself exploring a fascinating world beneath the surface of the ice. This intricate structure holds hidden liquid pathways, teeming with biological activity that plays a vital role in polar marine environments. Ice, in its complex form, can fracture in response to even the smallest seismic events. As temperatures plunge, large sheets of ice on lakes, rivers, and coastal areas undergo a dance of expansion and contraction. When the internal stress of these sheets becomes overwhelming, the surface can crack with astonishing force. The sudden release of tension sends vibrations racing through the ice, traveling into the water and ground beneath. Sensitive instruments placed near frozen bodies of water often detect these occurrences as tiny quakes, as the energy moves in a way similar to seismic waves. If you find yourself standing on or near the ice, you might hear booming, rumbling, or whipping sounds echoing across the surface. In vast expanses, these fractures can stretch for remarkable distances, creating visible lines that connect one shore to another. Each event is influenced by the thickness of the ice, the pace of temperature changes, and the movement of water below. Every fracture serves as a reminder that these frozen landscapes are alive, constantly storing and releasing energy in ways that mirror much larger geological processes. This dynamic environment invites you to reflect on the powerful forces at play in the world around you. Winter storms have a fascinating ability to create rare spherical ice pellets. When powerful cold season storms draw in moist air, it travels through freezing layers of the atmosphere, leading to the formation of unique precipitation. These small, round pellets are made from tightly packed ice. They develop when supercooled droplets collide and freeze around a central particle. As these pellets tumble through turbulent air, more droplets cling to them and solidify, transforming into smooth spheres instead of jagged crystals. Unlike hail, which forms during warm season storms and requires strong updrafts, these pellets emerge at lower altitudes. They also differ from sleet. Their internal structure is layered and dense rather than solid throughout. When these ice pellets reach the ground, they bounce instead of shattering, producing a distinctive sound as they hit hard surfaces. Such events occur only under a specific combination of temperature, humidity, and atmospheric movement, making them a rare feature of winter weather. Their formation unveils the intricate complexity hidden within storm clouds, where water and ice interact in ever-shifting conditions. Take a moment to reflect on the wonders of nature. Isn't it remarkable how such delicate phenomena can emerge from the chaos of a storm? Snowpack conceals vast amounts of water that can release suddenly in spring. As snow accumulates throughout winter, it traps significant quantities of frozen moisture within its layers. Over time, the density of snow changes as the grains fuse and settle, hiding considerable water content beneath what might seem like a soft, lightweight surface. In areas with heavy winter snowfall, this stored moisture becomes a vital contributor to rivers, lakes, and groundwater once spring arrives. When temperatures rise quickly, meltwater can flow faster than the soil can absorb it, leading to rapid increases in stream levels and sudden flooding. Mountain regions are particularly sensitive to this phenomenon, as elevation changes affect how quickly different slopes warm. As the snowpack melts, its internal pathways also shift, creating channels that guide water downhill in concentrated flows. Scientists keep a close eye on snow depth, density, and temperature to predict how much meltwater will enter watersheds. These predictions are crucial for managing reservoirs, assessing flood risks, and planning for agricultural needs. Thus, snowpack is not merely a seasonal decoration, it plays a significant role in our ecosystem and water management. Imagine a vast temporary reservoir playing a crucial role in the annual water cycle. Frozen lakes can encapsulate methane in shimmering clear domes. When organic matter decomposes at the lake's bottom, it releases methane that gradually rises to the surface. During the warm months, this gas escapes freely into the atmosphere. Yet in winter, a thick layer of ice prevents its release. Beneath the frozen surface, gas bubbles accumulate, pushing upward and stretching the ice into beautifully curved, transparent domes. These domes vary in size depending on how much gas is trapped and the ice's strength. In certain regions, you might find dozens, even hundreds of these structures across a single lake, creating a landscape adorned with glass-like bubbles suspended in sheets of ice. The trapped methane forms patterns of stacked circles within the ice, each one a unique pulse of gas. As spring arrives, the ice begins to break apart, allowing the gas to finally escape. Researchers observe these formations to gain insights into methane emissions and to monitor how lake ecosystems evolve during winter. These frozen domes serve as natural archives, preserving a record of biological activity that continues quietly beneath the ice. Birds adjust their flight patterns as winter approaches. With the drop in temperature, cold air becomes denser, providing increased lift for their wings and altering the flow of air around their bodies. Many species adapt their wing beats, gliding intervals, and flight paths to make the most of these seasonal changes. In winter, some birds can glide over longer distances with less energy since the denser air offers stronger support. Others find the optimal altitude where their flight efficiency peaks. Even minor shifts in air density can influence how flocks move together, impacting their spacing and the stability of their formations. Birds migrating through colder regions must navigate these changes as they embark on long journeys. The mechanics of their flight shift subtly, requiring them to modify their behavior to maintain speed, conserve energy, and avoid turbulence. Each movement reveals their deep understanding of the invisible environment that surrounds them. Winter also affects how radio waves travel. The atmospheric layers during this season can become stratified, creating sharp temperature differences between the ground and higher altitudes. This intricate dance of nature invites you to consider the unseen forces at play in our world. If you wish, take a moment to reflect on these connections or continue exploring. Imagine layers of the atmosphere guiding radio waves along curved paths, allowing them to travel much farther than usual. When cold air sits beneath warmer air, this creates a reflective boundary that helps radio signals bounce horizontally instead of drifting upward into space. This phenomenon can enhance communication signals over vast distances, particularly on winter nights. As humidity decreases and the air becomes clearer, certain frequencies can travel with less interference. These conditions can lead to surprising receptions of distant broadcasts, sometimes reaching hundreds of miles from their source. Engineers and researchers delve into these seasonal changes, aiming to enhance communication systems and better understand how the structure of the atmosphere influences signal pathways. Winter, with its distinctive temperature gradients, acts as a natural laboratory, unveiling the intricate interactions between electromagnetic waves and the environment. Picture fresh snow glowing softly under ultraviolet light. The surface of this pristine snow is composed of countless tiny ice grains that scatter light in a myriad of directions. When exposed to ultraviolet radiation, some of these grains reflect and refract wavelengths, producing a delicate glow that becomes visible under the right conditions. Take a moment to ponder this fascinating interplay of nature and technology. Would you like to explore more about how our environment shapes our experiences? You notice that this glow remains hidden from view in regular daylight. The brighter wavelengths wash over the ultraviolet reflection, masking its presence. However, in controlled settings or under the crisp ultraviolet light of high-altitude winters, the glow becomes strikingly apparent. Its brightness varies based on the purity of the snow, the shape of the grains, and the quality of the light source. Researchers delve into this phenomenon, seeking to understand how snow interacts with radiation and its impact on the energy balance at Earth's surface. Consider smoke that glows under ultraviolet light. It exemplifies the intricate ways frozen water can manipulate electromagnetic energy. What seems like a simple white surface is in fact a highly reflective structure capable of scattering a broad spectrum of wavelengths. Ice crystals in clouds possess an extraordinary ability to float for extended periods without descending. Under specific conditions, tiny crystals form in cloud layers, where temperature, humidity, and air motion remain remarkably stable. These crystals are incredibly light and often take on shapes that increase drag, effectively slowing their fall. Gentle upward currents within the cloud can counteract gravity, allowing these crystals to remain suspended for long durations. As you reflect on these intricate processes, you might find yourself curious about the hidden wonders of nature. Would you like to continue exploring, or perhaps take a moment to pause and absorb this fascinating information? As you observe the world around you, suspended crystals continue to grow by drawing in water vapor from the air. Some of these crystals linger in the atmosphere until they merge with others or enter areas where air movement shifts. Their extended presence influences cloud brightness, the formation of precipitation, and how sunlight interacts with the sky. Scientists carefully study these suspended crystals to gain insights into cloud dynamics and improve weather forecasts. These tiny traces help reveal how air flows within storm systems and high-altitude cloud layers. Imagine the impact of winter temperature fluctuations on stone. Rock surfaces expand slightly when warmed by sunlight and contract under the chill of freezing nights. Over time, these cycles create microscopic cracks that open and close, gradually weakening the outer layers of the rock. When water seeps into these cracks and freezes, it expands, further widening the gaps and lifting small flakes from the surface. This natural process can lead to the formation of grooves, pits, or channels, marking the stone with patterns shaped entirely by temperature changes. These features develop more quickly in regions where winter brings swift transitions between warm afternoons and cold nights. Take a moment to reflect on the beauty of these natural processes. Would you like to continue exploring, or perhaps take a moment to rest? Different types of rock respond uniquely to their mineral composition and any structural weaknesses they may have. These changes unfold slowly, yet persistently, showcasing winter's ability to reshape solid materials through repeated thermal stress. The resulting patterns become historical records, telling the story of the environmental conditions that shaped them. Snow cover significantly alters Earth's reflectivity. When large areas are blanketed in bright, fresh snow, they reflect a substantial portion of incoming sunlight back into space. This increased reflectivity cools the surface and influences the temperature of the air above. When snow persists across vast regions, it plays a crucial role in the global energy balance, affecting how much solar energy our planet absorbs. Even minor changes in snow extent can impact regional climates by modifying the heat exchange between land and atmosphere. Scientists closely monitor snow cover because it interacts with cloud formation, storm tracks, and long-term climate trends. Snow serves as both a shield that deflects sunlight and a regulator that controls surface heating. Its presence or absence can determine whether cold conditions intensify or weaken. As you reflect on this, consider how interconnected our world is and the subtle yet profound ways that snow influences our climate. Would you like to explore more about this fascinating topic, or perhaps take a moment to rest? Winter landscapes play a significant role in influencing temperature patterns across vast regions far beyond their immediate surroundings. Ice forms layers that encapsulate decades of atmospheric chemistry. Each year, as snow settles and gradually compresses into ice, it traps tiny samples of the atmosphere from the time of its formation. Within these layers, you can find traces of gases, dust, pollen, volcanic particles, and even microscopic organisms that floated through the air. As more layers accumulate above, the ice transforms into a chronological archive, preserved under cold and stable conditions. Scientists use long cylinders called ice cores to extract and analyze these layers. Each one reveals insights into past temperatures, atmospheric composition, and significant environmental events, such as forest fires or distant volcanic eruptions. Some ice cores reach back centuries, enabling researchers to reconstruct long-term climate patterns. The chemical makeup of each layer offers clues about ocean circulation, solar activity, and changes in vegetation. Ice serves not only as a physical substance, but also as a vital record keeper, holding the stories of our planet's climatic history. Music captures details that no instrument can measure in real time, preserving them for generations. It offers a unique glimpse into the history of Earth's atmosphere. You might notice how winter air alters the taste of food. Cold, dry air changes the way aromas travel from your plate to your nose, which directly affects your flavor perception. Aromas depend on volatile compounds that evaporate easily in warm conditions. When the air turns cold and still, fewer of these compounds rise from your meal, leading to a diminished scent. Since a significant part of what you perceive as taste comes from smell, this reduction in aroma makes certain foods feel less intense. Interestingly, cold air can enhance your sensitivity to specific flavors. With your mouth and nasal passages remaining cool, there's less interference from humidity. You can especially notice this during winter activities, outdoors or in homes where drafts are common. Foods that usually feel rich may taste muted, while sharper or saltier items can stand out more prominently. The environment around you plays a crucial role in your experience. A warm drink tastes more robust when held in cold air because the steam carries aroma directly upward. However, a cool dish might seem bland as its scent stays close to the surface. As you reflect on these experiences, consider how the simple act of eating can be transformed by the elements around you. Take a moment to appreciate the nuances of flavor and aroma in your next meal. Winter has a profound effect on flavor, altering the physics of odor molecules and how your senses engage with the environment. Frost can emerge from warm objects, creating a fascinating interplay. When a warm object is placed in very cold air, moisture from the surroundings condenses on its surface and freezes. As heat gradually escapes from the object, the frozen layer thickens. Simultaneously, new moisture from the air settles on the diminishing warm boundary around the object, freezing just outside the previous layer. This cycle continues, resulting in delicate icy fingers that stretch outward, sometimes forming long feathery structures that reach into the air. The configuration of these formations is influenced by airflow and temperature variations. When air flows consistently in one direction, frost resembles a miniature forest, leaning toward the breeze. In contrast, if the air remains still, the frost develops a more symmetrical pattern. You often notice frost forming on pipes, wires, and vents. These surfaces emit enough warmth to attract moisture, while still being cold enough to allow freezing. These intricate growth patterns reveal the delicate balance between heat loss, humidity, and surface temperature. Frost serves as a vivid reminder that it is an active process, influenced by the movement of energy rather than merely a static layer. In winter, water can freeze into remarkable column structures that appear almost man-made. Under specific conditions, water freezes into vertical columns instead of forming a flat sheet. This phenomenon occurs when cold air rapidly penetrates the ground from above, while the soil below still holds liquid water. As the surface freezes, ice crystals grow downward, drawing water upward through narrow pathways. This upward flow continues until the crystals extend into parallel columns, sometimes reaching several centimeters in height. These striking structures resemble tiny pillars or raised platforms capable of lifting stones, soil, and even plant material as they rise. The result is uneven terrain that crunches underfoot. The formation of these columns relies on various factors, including soil moisture, temperature, and the rate at which heat escapes from the ground. When cold conditions persist, the columns become more pronounced. However, if temperatures fluctuate, they may collapse, leaving scattered fragments on the surface. These formations reveal how freezing can transform the landscape, creating patterns that seem almost engineered. Sea ice serves as a unique habitat, hosting intricate microbial ecosystems. In the polar regions, ocean surfaces freeze into expansive sheets, forming networks of brine-filled channels within them. These narrow pathways hold salty liquid water that remains unfrozen even in the harshest cold. Microbes specially adapted to low-light, scarce nutrients and freezing temperatures thrive within these channels. They create communities that feed on dissolved organic matter and support small organisms that graze on them. As sunlight begins to filter through the ice during late winter and early spring, photosynthetic microbes spring into action, producing energy that fuels further growth. These vibrant ecosystems play a vital role in nutrient cycles within polar oceans, releasing essential compounds into the water below. When the ice eventually melts, the entire community flows into the ocean, triggering bursts of biological activity that impact the food webs. Despite the extreme conditions, these tiny organisms establish stable ecosystems within structures that may seem solid and lifeless from the surface. Their existence highlights that ice is not merely frozen water, it is a dynamic habitat capable of sustaining life with remarkable resilience. Even frozen waterfalls can capture the sound of flowing water beneath, adding to the mystery of this hidden world. As the temperature drops swiftly, the outer layer of a waterfall freezes, while the water within continues its relentless flow. This movement carves out tunnels, sheets, and hollow chambers in the ice. These pockets capture sound, reshaping it as it echoes through the frozen layers. The result is a symphony of tones that starkly contrasts with the thunderous roar of an unfrozen waterfall. Deep, resonant hums blend with the lighter tapping sounds produced by the vibrations of thinner ice. With every shift in temperature, new cracks form while old ones close, altering the acoustic landscape. If you stand near these formations, you can hear the water rushing beneath your feet, even as the surface remains eerily still. The frozen structure transforms into a natural instrument, its acoustics constantly evolving. This phenomenon beautifully illustrates how freezing can separate moving water from its environment, while allowing its energy to resonate invisibly through the ice. Snow, too, plays a fascinating role. It can convert sunlight into heat through subtle chemical reactions. While snow reflects much of the sunlight that touches it, some wavelengths manage to penetrate the upper layers. When this light meets impurities embedded in the snow, like organic molecules or dust particles, tiny chemical reactions unfold, revealing the hidden complexities of this frozen world. Take a moment to reflect on this interplay of nature, where sound and light converge in unexpected ways. Would you like to explore more about these natural wonders, or perhaps take a moment to pause and absorb the beauty around you? These reactions release small amounts of heat, gently warming the surrounding grains. This warmth may be subtle, yet it significantly influences how quickly snow reshapes or melts. In areas abundant with natural or wind-blown organic matter, these reactions play a vital role in the seasonal shift from winter to spring. The interplay between sunlight, snow grains, and chemical impurities creates microenvironments within the snowpack, which differ from the colder layers surrounding them. Researchers delve into these effects to understand melt rates, surface chemistry, and how snow transforms into firmer granular forms. Snow is not merely passive under sunlight, it actively engages in energy exchange through reactions that shape its seasonal evolution. During winter storms, powerful winds can sculpt sand and soil into entirely new formations. The dry particles move across the ground, carving them into ridges, ripples, and intricate shapes. When temperatures remain below freezing, moisture within the soil acts as a stabilizer, allowing for more detailed shapes to emerge than during the warmer seasons. Snow mixed with sand can create layered structures that seem as if they were crafted by hand, revealing the artistry of nature in the cold. Even the gentlest breeze can etch patterns across the open ground, while more intense storms carve features that endure through the winter. These formations offer insights into wind direction, strength, and duration. In coastal areas, winter storms unveil hidden layers of sediment by sweeping away loose particles from the surface. Meanwhile, in desert landscapes, cold air helps sand grains settle into temporary shapes, which disappear once warmer weather loosens their grip. The winter landscape transforms into a canvas, molded by the interplay of frozen ground and relentless wind. When temperatures dip well below those of nearby objects, cold air reveals heat signatures that remain hidden at other times of the year. Subtle sources of warmth, such as buildings, vehicles, trees, and even buried pipes, emit heat into the frigid air. These temperature variations create visible patterns when viewed through thermal imaging, uncovering details that elude our gaze in warmer seasons. Wildlife trails become more apparent as animals leave warm traces in the snow or air. Human activity also stands out, with footprints, exhaust, and body heat forming distinct thermal signatures. In this captivating winter world, the interplay of elements creates a tapestry of life and movement that invites you to explore further. So, take a moment to reflect on the beauty around you and consider what hidden stories the winter landscape might reveal. Researchers delve into winter conditions to explore how heat dissipates in structures, track animal movements, and examine the flow of warmth through soil and vegetation. The chill of winter enhances thermal contrasts, transforming the landscape into a vivid map of energy transfer. This season offers a distinct lens through which you can observe the dynamics of heat in both natural and human-made environments. As ice forms, it can fracture rock through repeated cycles of freezing. Water seeps into tiny cracks in stone, and when temperatures drop overnight, it freezes and expands. This expansion exerts enough force to widen the cracks. When this process occurs repeatedly throughout the winter, it can gradually pry apart layers of rock, eventually breaking off pieces. While this transformation happens slowly, it is relentless. It reshapes cliffs, boulders, and exposed rock faces. The freezing water creates wedges that push outward with remarkable strength. Over time, rocks begin to fracture along their natural weaknesses, leading to debris accumulation at the base of slopes. In areas that experience frequent freeze and thaw cycles, this phenomenon plays a significant role in creating loose stones and soil, contributing to the long-term sculpting of mountains and valleys. Take a moment to reflect on these intricate processes. They remind us of the profound impact that winter has on our environment. Would you like to continue exploring, or perhaps take a moment to rest? As winter unfolds, each cycle brings subtle changes that accumulate over the seasons. You witness the remarkable ability of winter to reshape even the toughest materials. In these chilly landscapes, nature crafts unique acoustic amplifiers. When snow, ice, and cold air blend in just the right way, entire terrains transform into giant sound-shaping structures. Fresh, dry snow absorbs high-pitched sounds while reflecting lower frequencies, creating pockets where certain noises become remarkably clear. The smooth ice of lakes efficiently reflects sound, allowing vibrations to travel long distances across its surface. In valleys filled with cold, dense air, sound can become trapped, guided along narrow channels between the walls. Even the frozen forests play a role, as stiff branches transmit vibrations differently than their flexible summer counterparts. In moments of perfect stillness, temperature inversions create layers of warm air above the cold ground. Sounds that would usually rise into the sky instead bend back down, magnifying distant noises. A crack in the ice, a distant animal's call, or the faint sound of a single footstep can suddenly feel unnaturally loud. In these winter environments, you find temporary acoustic chambers formed entirely by temperature, density, and surface texture. Each element contributes to a unique auditory experience, inviting you to explore the beauty of this transformed world. Winter transforms open spaces into vibrant stages where sound dances in unexpected ways, unveiling the hidden shapes of the musical landscape. Beneath the frozen tundra, ancient forests lie preserved, a testament to the passage of time. In the cold northern reaches, the ground can remain frozen for thousands of years, encasing entire ecosystems in its icy grip. Long ago, lush forests of spruce, birch, and other species thrived in areas that are now barren tundra. As climates changed and temperatures plummeted, these forests receded, buried under layers of sediment, peat, and ice. The frozen ground protects these remnants from decay, halting microbial activity and keeping oxygen at bay. Tree trunks, roots, leaves, and even seeds can remain remarkably intact beneath the surface. Researchers delve into these buried forests, examining the shapes of roots, the wood's composition, and the surrounding soil to reconstruct ancient landscapes. Some sites reveal clear signs of past fires or insect activity that occurred before the freeze. These frozen remains stand as records of the climate changes that have unfolded over millennia. As you reflect on this, consider the stories that lie hidden in the cold, waiting to be uncovered. Would you like to continue exploring this fascinating world, or perhaps take a moment to rest? You witness the remarkable ability of ecosystems to transform and the way cold environments